Hello, we will discuss now some tools designed in view of extracting useful visual information from the results of a SIESTA calculation. We will now consider the scripts aimed at elucidating the crystal structure information, properties defined on the grid, and lattice vibrations. Now I intend to present you two sets of post-processing tools designed to extract useful and visual information from SIESTA calculations. This information relates in particular to crystal structures, to lattice vibrations, and to identifying properties calculated on the grid. There are two systems of tools known under the name of CS2XSF and the smaller and more recent one, which is called XV2Vesta. The oldest one exists already since quite a time, and it has been presented at earlier SIESTA schools and tutorials and documented in the files, the addresses to which are indicated here on the page. And quite recently, within the publication devoted to recent development of applications of SIESTA, also the role and the possibilities of these tools has been mentioned. In particular, and what regards the CS2XSF suite, this is the selection of tools which are intended to translate the information from SIESTA files into the format proper to the XCrisDen software. And in particular, there are 5 tools which have been written in Fortran, and they can be easily compiled and linked within the package as they are provided. And the purpose of these tools are: the first one serves just to visualize the crystal structure and to check that the position of atoms and the structure information is correctly grasped for the calculation. Then the next one, row to XCF, serves to translate the property calculated on a grid, such like charge density or potential or local density of states, to the format proper to XCrisDen. Then the third tool serves to visualize the vibrations which result from the Vibra calculation on top of preceding SIESTA calculation, right? And this can be done either in a static way, by just attributing arrows to the atoms, or by creating an animated movie which shows how the atoms vibrate. Then yet another tool serves to construct the movie from the data of molecular dynamics, either MD or ANI file. And finally, there is an option to plot the Fermi surfaces, starting from the information about band energies and key points. The native format of XCrisDen software is XSF, and another useful software which I will mention, which is called Vesta, is also permits to read directly this XSF format for the crystal structure information. This XCrisDen software has been originally created and maintained by Tony Kokal, and it has been used on very many occasions in scientific publications. So this is a very flexible tool, which is also free for the non-commercial use. So this is a tool which is highly appreciated by many colleagues. And another software, Vesta, is being maintained by Koichi Moma, This tool is very strong in what regard the crystallography, manipulating the structures, and also the graphical quality of results which are generated is also very impressive. So these are a good reason for using either of these tools. Then how to use the tools of the CS2XSF suite. In fact, they can be run just on the command line, starting them from the terminal, and then passing all the necessary parameters as prompted. So there is no graphic interface, no options to memorize, so this is relatively self-explaining. One should mention that for some of these tools, one has to define a visualization box. That is the volume or the shape within which the atoms will be selected and visualized. This box does not need to be identical or anyhow related with the unit cell or the supercell used in the calculation, and one just need to know how to define the size, the position of this box. This is done by the reference point and giving the 3 axes which pass through this reference point, and specifying further on the distances along this axis to the positive direction, to the negative direction. We just cut the size of the cuboid which will serve the role of our visualization box. We will see further on in the examples how this works. And as for the Fermi surface calculation, one should mention that we need the band energies calculated on fine enough grid, and this K-mesh grid has to be non-shifted. That means that the gamma point should be explicitly included into this grid. Well, then a smaller package exists which translates information from SIESTA directly to the native format of the VESTA package. In fact, this smaller package, smaller suite consists just of 2 tools. XV to VESTA just transforms the crystal structure information, and VIP to VESTA transforms the vibration. And if the first tool in fact is not so necessary, because VESTA can directly read the data in the native format of XCRISDEN, then for vibrations this indeed makes sense because the VESTA package offers much more flexibility in assigning properties to arrows and placing the arrows, attributing them colors and thickness and so on and so forth. So this becomes a very powerful tool which permits to create very nice figures visualizing the vibrations. So then we will pass to the discussion of some examples of how to use these tools. We consider now some examples of using these tools and viewing the results of the analysis with the XCRISDEN or VESTA. We start with the simplest example of just visualizing the structure. In this directory we have a XV file which we want to transform into XSF format. In fact, we just run the script and we pass the name of the file. Then we should confirm to overwrite this resulting file, and then we can visualize the structure with the XCRISDEN. We open this file. Okay, so we see this is in fact a layer structure with some adsorbed atoms. In order to see it better, we just double it in the Z direction. Okay, then we clearly see the structure of this system, and then we can modify it as we wish using just the options provided in the xcrisden file. And we see that okay, this is the regular layer, and atoms which are situated in some distance. Voilà. Now, if you want to see how the same file will look like when loaded into SIESTA, so okay, so this is the way it looks like in SIESTA, right? So again, there are different options how one can choose the size of the part of the system to show, how to connect the atoms by choosing the chemical bonds, and so on and so forth, how to measure the distances, and so on. So this is just an example how the XSF file can be directly read into SIESTA. Okay, our next example is that of a property calculated on the grid. In this directory we have the charge density file, and we will plot it, or more precisely we will plot the magnetic density. Right? So in order to create or to recreate XSF file with the script, I just run the script rho2xsf. Okay, then I pass the generic name of the file rfm01. Yeah? So this is generic name of the file xv and rho. Then I have to make some definitions. So I choose the angstrom as a unit of length. Then I define my reference point for choosing the visualization box. Then I define the first axis, and the size of the visualization box measured along this axis will be from -8 to 8 angstrom. Then I do the same for the second axis. So this is more or less arbitrary, but I just repeat it like this. And then for the third axis, and I do the same. And then I confirm to overwrite the file which already existed before. And finally, I need to define the number of grid points, right, for my visualization with the xcrisden. So I just pass 3 numbers, large enough to have defined mesh, and I confirm the properties. So this is raw. Okay, so this is interpolated read, and that's it. So this file has been created, and now I can run xcrisden and open this file in xcrisden. So I go and open rfm01.xsf. So this is a file which shows well, the structure. Well, in fact, it's a kind of finite cluster and so on, cubic shape. And we want to show the charge density, right? In order to see charge density, I go to Tools, and I choose Data Grid, and then I identify that I want to add 2 components. So the spin up, I will take it with the weight 1, and the spin down, I take it with the weight -1, and I submit, right? And then finally, to get the image, I need to identify the ISO value. So I will say take something like this, and then I submit. Okay, and I see some fragments of the surface, and in order to see it more pronounced, so I reduce the level of the contour So this gradually becomes less and less. Okay, so then I can choose the way to show my atoms. It will be shown just by sticks without balls, right? And so, okay, so this is the arrangement of positive and negative charge density. Well, and then it can be further on analyzed, printed out, and so on. Now, as a final example, we consider visualization of vibrations. In this directory, we have the structure file of a semiconductor, of chalcopyrite structure, and the results of gamma phonon calculations, namely the vectors file. Now we want to select some of the phonon modes and make a picture and make an animation of these modes. Then I run VIP2XCF. I confirm the SIESTA, because this is the label of XV file. And then I define the visualization box as I did before. More or less I do the same. So I define the reference point. Then I choose the vectors, the second direction along the y-axis, and then the third direction, something like this. And then I need to confirm the system label for vibrator calculation, which in this case is called Vibra. So, and then I need to identify the modes, and totally there are 48 modes. So I'll just take the two final ones, 47 and 48. And then I identify the amplitude of displacement for animation, for the visualization, and I define the number of steps. Okay, then apparently these figures already existed, so I need to confirm overwriting them, and that's it. So this is done. Then open XCreaseDen. Open XCreaseDen, and I can open the animation. Animation, I have the mode number 48, and the animated file is with the extension AXSF. Right. So there are the atoms which has been selected in my visualization box, and voila. So this is how it moves. So I can change the orientation of the fragment and still have the visualization. Okay, this was the dynamic way of representing vibration. Otherwise, I can choose the static way. So open XSF file for the same mode, and then I need to display forces. So something. Switch it on and off. Voila. So now my directions of the atomic movement are indicated by arrows, and then I can modify the properties of these arrows and well, make them longer or shorter, and then choose the way to export this result.